Hello to our friends joining us via recording. We are reviewing for exam number 1. Exam number 1 is open right now, September 21st, Monday, September 21st, and it closes tomorrow. That's Tuesday, the 22nd at 11:59 p.m. So you've got 2 days to get that exam taken. We're going to review some of the most important topics from that Unit 1, the stuff that's going to be on the exam. One of the things that a lot of us said we were really interested in talking about was the membrane, the structure of the membrane, the way it lets things in and out. So we're going to start by talking about the membrane. When I talk about membrane, here's my first question for my friends here in class. When I talk about the plasma membrane, can you tell me what these little things that it's made out of are called? What are these little guys that it's made out of called? These little things with a circle and these little lines. Yeah, so the circle part's the head. Yeah, it's a big long word, isn't it, right? That it was kind of mean for me to ask that. I know that was mean, sorry. The name of the whole thing with the heads and the tails, those things are called phospholipids. Remember that the plasma membrane is called the phospholipid bilayer. So it has 2 layers of phospholipids. So the phospho part of its name comes from the heads. So phospho part of its name is referring to the head part of the phospholipid, and the tails are the parts that are the lipids. Yeah, so a couple of us mentioned in the chat this phospho part, the head part. The reason I use this part phospho is because it has a phosphate group. The big thing I told you to remember about the phosphate group of a phospholipid is that it has a negative charge, or that this part of my phospholipid, it does play nice with water. What's that word for I really like water? Actually, there's a couple of words for I really like water. Yeah, so the first word for I really like water is called hydrophilic. Hey, if something is hydrophilic, yeah, a couple of us are chiming in the chat. The other thing that I can say that it is it's polar. Hydrophilic and polar both mean that it plays nice with water. The head group portion of my phospholipids, so the little circles that I see here and the little circles that I see here, both of these parts of my phospholipid bilayer are hydrophilic. Both of them are polar. Yeah, because they share their charges unequally. Yep, that's what polar means. So when you look at the structure of a phospholipid up close, they'll actually even put a little negative charge on the phosphate. So unequal charge across the parts of this head group. That's what makes it polar. That's what makes it hydrophilic. The tail portion of these phospholipids, these little lines that I see inside here, these are lipids, which is a fancy word for fats. What word would I use to describe the relationship between fat and water? How do fats or lipids feel about water? Yeah, so a couple of us are chiming in with our hydro word, hydrophobic. Hydrophobic would be one way I describe them. I like that someone else mentioned too that the idea of lipid soluble. I will come back to that word because that's important for us. The other way I would describe these lipids is nonpolar. Remember that hydrophobic and nonpolar are synonyms for each other. Hydrophilic and polar are synonyms for each other. So any part of this plasma membrane, which is everything I see here, any part of it that I say is hydrophilic, I could also say is polar. Any part that I say is hydrophobic, I could also say is nonpolar. So what we did a lot during our office hour times together is we color-coded things. So for example, when I talk about the parts that are hydrophobic, I'm going to do some squiggles in here. These portions here in the middle with my lipid tails are my hydrophobic parts. I would also, though, if I decided that my nonpolar things would be green, the parts of my membrane that I say are nonpolar are going to be those same parts of the membrane that I said were hydrophobic. Because again, those words are basically synonyms for each other. And when we talk about something that's hydrophilic, meaning it loves water, that's going to be these guys here on the outside. Drawing a big line here, bear with me. I did pretty good on that line. And then we've also got these guys here in the middle. Okay, those are hydrophilic, and we could also then make our polar stuff blue. The blue and the red overlap. Big idea is the blue and the red overlap. Polar and hydrophilic always overlap. And non-polar and hydrophobic, they always overlap. When I talk about the phospholipid bilayer, these two layers of phospholipids that come together to make a barrier to the outside, is it the heads or the tails that decides what can get through the membrane? Who decides what gets through, the heads or the tails? Yeah, lots of us lighting up the chat. It's these tails here in the middle that decide what does and does not get through. We're too messy here. Let's clear it off. If the tails are what decides what gets through, what are the words we would use to describe the kind of things that can get through the membrane? What are those chemistry words I described for the things that could diffuse across the membrane? Okay, so we're in the right genre. We're talking about, so let's list the words that we got so far. In the chat, I've seen polar, I've seen non-polar, I've seen hydrophobic. I haven't seen it all yet, so I'm going to type it in here anyway. I'm sure somebody will say it eventually. Hydrophilic. Somebody did mention large. Let's talk about these words that we have right here. Oh yeah, there's another one. Here we'll add lipid soluble. And while we're at it, we'll say water soluble. Yeah, a lot of us in the chat are like, oh my gosh, I'm so confused. That's because I'm listing all the answers that we put, and not all of these answers are correct. So we're going to go through and we're going to figure out which of these types of things can and cannot get through the membrane. When I talk about what can and cannot get through the membrane, it does have to do with these tails. So yeah, someone asked, what was the question again? The question that we're going to answer together as a group is, what kinds of things can get through the membrane? That's where we're going. That's our goal, is to figure it out. So these are all, we made an exhausted list of all the kinds of things that I could ask you about whether or not it could get through the membrane. So we're going to work together as a class to figure out what can and can't get through the membrane. So you guys told me before that the tails help to determine what is allowed to get through the membrane. I do or don't match the tails if I can get through the membrane. I do or don't match the tails if I can sneak straight through. Yeah, so a few of us are chiming into the chat. If I can sneak through the membrane, I do match these tails. I have to be the same as these tails. If I'm the same as these tails, I can sneak right through the membrane. I can get inside or I can get outside. The tails like things that are like them, don't like things that are not like them. So if you don't match the tails, no go. You're not passing through the membrane. So let's start with our first set of words up here. When we talked about the tails, did we say that the tails were polar or non-polar? What were my tails? Polar or non-polar? Yeah, a couple of us remember. My tails are non-polar. Non-polar. Here, let's do a little chemistry review. When I talk about something that has a non-polar covalent bond in it, what's going on in a non-polar covalent bond? There are lots of different things we can say about these bonds. What happens in a non-polar covalent bond? Perfect. Two big ideas for us to remember. First idea for us to remember, nonpolar covalent bonds, they're a covalent bond, so they're a sharing bond. That's the first thing we always got to know. Here, we'll put covalent in parentheses here. Covalent, sharing bond. Second thing we need to know, since it's nonpolar, like you guys told me, it's equal sharing. Let me make that in caps too, because that's important. Equal sharing. So when we do a nonpolar covalent bond, which is what we see here in the middle with these lipid tails, since they're nonpolar, they've got nonpolar covalent bonds in them. That means the way that I hold these things together is they're sharing. And it is important, I'll type this on here too, because several of us said this in the chat too. It's important to note that what I'm sharing is electrons. Whenever I make chemical bonds, it's always electrons. It's not protons, it's not neutrons, it's always electrons. So, nonpolar covalent bond is a sharing bond. I share my electrons, and because it's nonpolar, I share them equally. And so a couple of us mentioned this in the chat. Another important idea about nonpolar compounds is they have no charge. There's no charge. None of those things, I'll add this here to our list about polar things. If I'm nonpolar, I do not have things called dipoles. Dipoles are something that only polar compounds can have. Can anyone help me out and explain what a dipole is? Or maybe it's easier to explain, how does a dipole form? What are they, or how do they form? Okay, so yeah, it is something I form with polar covalent bonds. Yeah, so with polar covalent bonds, it's still a sharing bond, but it's not equal sharing. So polar, we have not equal sharing. And like a lot of people are talking about in the chat, when we're saying the dipoles, it's partial positive or partial negative. The way this happens, sorry, we're all scrunched up here. Let me draw a little line. The way this happens, getting a partial positive and a partial negative, is somebody in this bond gets the electrons a little more often than somebody else. We're not equally sharing those electrons anymore, which makes me have an area that looks a little bit positive and an area that looks a little bit negative. Hey, if I'm the part of an atom that gets those electrons a lot, if I get them more often, do I look positive or negative? If I'm the one that gets those electrons a lot, do I look positive or negative? Yeah, so a lot of us are agreeing. The part that sees the electrons more is going to be the part that has a partial negative charge, because electrons have a negative charge. The part that sees them less is going to have a positive charge because it's losing its negatives. Now all it has left is its positives. What were those positively charged particles called? What are those things in the nucleus with a positive charge? Yeah, so the things in the nucleus with the positive charge are the protons. And the protons are attracted to the electrons. That's why those electrons with their negative charges spin around in circles, trying to be close to the protons. We brought up a great term that's actually I'm gonna switch over to my other side of our picture over there where we're talking about ions. We had the terminology cations and anions pop up in the chat. What can you guys tell me about cations or anions? What are these? What's going on with the charges of these guys? Cations and anions. Perfect. Gloria got a couple of good descriptions here of our cations. So cations, first thing we need to know about them is they have a positive charge. Cations are positive. They form because we lose an electron. We lose it entirely. Somebody else gets it. The somebody else who gets it is my anion. They gain an electron. That's an anion. So anions have a negative charge. Negative charge. Now, here's sometimes in the office hours, I give you guys notes. I say to like underline, highlight, star this. So important idea here. An ion is different from a dipole. So a dipole is an area where it's partially positive or partially negative. When we talk about an ion, there's nothing partial about it. We are fully positive or fully negative. So ions are things that always have a positive charge or always have a negative charge. Dipoles are places where sometimes I look positive, sometimes I look neutral, or sometimes I look negative, sometimes I look neutral. The biggest difference between a polar molecule and an ion is that these polar molecules form with our sharing bonds. When we talk about ionic compounds, they form using ionic bonds. Remember from your lesson, the word that I like to use for ionic bonds, I call those stealing bonds. Stealing bonds. Somebody lost an electron and somebody grabbed it. So ions form with ionic bonds. Polar compounds form with polar covalent bonds. We're still sharing. So anytime you see the word sharing, that's covalent. Covalent, remind me in the chat, covalent bonds, strong or weak? Covalent bonds in general, are they strong or weak? Yeah, we're right. Covalent bonds are strong bonds. Covalent bonds are strong bonds. Sharing is caring, right? That's what they say. If we are sharing our electrons, we're making a strong bond, a strong attachment. Hey, if we are stealing electrons, when I put an ionic compound in water, ionic compound like salt, for example, what happens to that ionic bond if I put it in water? Yeah, it dissolves, falls apart. So when we talk about ionic bonds, we would say they dissolve, or in other words, fall apart in water. Ionic bonds fall apart in water because they're not strong, because it was a stealing bond. Somebody lost an electron, somebody gained an electron. Because we look different, we have opposite charges, we're attracted to each other. But the thing with water is, remember that water has dipoles. Water has partial positives and partial negatives. So if I introduce other positives and negatives, the only thing that held these guys together was positive or negative. It was that attraction. So if you put other attractions in there with water, they're going to fall apart. They're going to dissolve completely. When we talk about any kind of covalent bond, whether it's nonpolar covalent or whether it's polar covalent, anytime we talk about a covalent bond, we're always sharing electrons. We're always in a, think of it as a committed relationship. We're sharing something together with each other, which means I've got a lot of stuff holding me together. If it's a polar covalent bond, if I have areas where I'm partially positive and partially negative, I might surround myself by water. I might like to be around water's dipoles, but I don't fall apart. I don't leave my other atom that I'm connected to, because we're sharing electrons. We've got electrons holding us together. If I'm sharing my electrons equally, I don't want anything to do with water's dipole. Remember from your guided lesson or from our class time together, we said, I don't need that kind of negativity in my life for water's negative dipoles, or I don't need that kind of positivity in my life for water's positive dipoles. If I've got no charges, if I'm in a non-polar covalent bond, I hate water. Water's got positives and negatives. I don't like it. If I'm in a polar covalent bond, sure, I might be attracted to water's dipoles, but I'm sharing electrons. I'm not going to leave my atom. Not like over here with my ionic compounds. With my ionic compounds, they're not sharing anything. It's just opposites attract. That's why ionic bonds fall apart in water, while our covalent bonds stay attached to each other. So crash course for us really fast in our bond types. Strongest types of bonds are those covalent bonds. Weakest types of bonds in terms of can you survive being placed in water? Those ionic bonds. They can't even. If they can't help themselves, if there's another positive or negative nearby, they're going to be attracted to that too. So ionic bonds versus covalent bonds. Ionic bonds are what form between a cation and an anion. But a cation and an anion, both of them types of ions here, they have those permanent charges, like you guys told me, a permanent charge. Ions, cations or anions, are these able to sneak straight through the membrane? Can ions diffuse into or out of the cell? Yeah, ions cannot. So we're gonna put a little X on our ions here. Ions cannot diffuse straight into or out of the cell. If you have a positive or a negative charge, these tails inside here say, no, you don't match me, and they will not let those ions pass through. So ions can't get across the membrane. We said that non-polar things can. Since non-polar and polar are opposites, do we think that polar things can or cannot go straight across the membrane? Can polar things sneak through? Yeah, polar things can't sneak through either. We're crossing those guys off. Hey, was hydrophobic or hydrophilic? So here, I'll help you out. For in the chat, we're either going to type phobic or philic. Was it phobic or philic that meant the same thing as polar? Which one means the same thing as polar? Phobic or philic if I'm polar? Yeah, philic. Philic means the same thing as polar. If polar things can't get across, hydrophilic things can't get across either. That word hydrophilic, again, let's fill in on our chart here. What does hydrophilic mean? Hydrophilic, what does that mean again? Perfect, yep. Water loving, or to map with one of our words on the other side of the picture, the other thing that hydrophilic means is water soluble. Water soluble. This word soluble here means that I can surround myself by water. If I'm hydrophilic, if I love water, yeah, I can surround myself by water. So things that are water soluble, also known as hydrophilic, also known as polar. None of those three categories, I'm going to cross out water soluble over there, none of those three categories can get across the membrane because they play nice with water. And remember, this middle part of the membrane does not play nice with water. Hey, hydrophobic. What does this hydrophobic word mean again? What does hydrophobic mean? Y'all type too fast because I like barely get to take a sip of my coffee before like we've got the answer in the chat. So props to you guys. I like the way that Aaron put it. This relates to my soul right now. No like water. No like water. Can't do it. I like that. Water fearing technically is what it means, or we kind of talked about it in classes like water hating. No like water. I like that. So if we're hydrophobic, we don't like water. We can't even with water. The word that we could use then from my other side that relates to that too then is we can also say that hydrophobic is the same thing as lipid soluble, as in I can surround myself by lipids and I can be happy because I don't like water and lipids don't like water. And while we're at it, non-polar things don't like water. So here's another thing that we'd circle that say would get across the membrane. Hydrophobic things, which is the same thing as, I guess circle it over here too, lipid soluble things, which is the same thing as non-polar things. Last category, or one last thing that we mentioned when we're talking about what can and cannot get across the membrane. If you're something that's particularly large, I don't even care if you're lipid soluble or non-polar. If you're really big, you're not going to be able to get through the membrane, because if we're too big, it's kind of going to blast a hole through this membrane. And if I don't have this membrane structure in place, we're going to have issues with water rushing in or water rushing out. So particularly large things can't get inside. Things that are called hydrophilic, they like water, they can't get inside. Things that are polar, meaning they have a partial charge, dice, can't come in. Things that have a full charge, things that are ions, cannot get in. At least not without us creating a tunnel or using some kind of protein, a transport protein, to get things inside. So when we're talking about what can and cannot diffuse across the membrane, and that's our keyword here, I'm going to type it at the top, we are talking about diffusion here, stuff that goes straight through the membrane. If you match the middle of the plasma membrane inside of here, you can do diffusion. You can go straight in, you can go straight out. If you do not match the middle of the membrane, you cannot do diffusion. You cannot go straight in, you cannot go straight out. We have to build you, let me draw us a little tunnel here. We have to build you a special tunnel for you to go in and out. That special tunnel makes a space for things that are water soluble, or a space for things that are hydrophilic, or a space for things that are polar. They can still get in and out of the cell, but they're going to have to use a protein to get them through, a carrier protein or a channel protein. We've got to use a protein to get those things in and out. So yeah, so the question we have in the chat, so diffusion does not require a transport protein. That is correct. Straight up diffusion, no protein required. Hey, what's it called if I do have to use a protein? If I'm still doing diffusion, but I'm using a protein to help me do it. What was that called? Do we remember? Yeah, so the protein is acting like a facilitator. So here, let's draw an arrow. Diffusion goes straight through the membrane. If we're using a protein to do diffusion, it would be called facilitated diffusion, when we use that protein channel to bring things through. So the best way I like to remember it is that the protein is a facilitator. It makes things happen. So facilitated diffusion, when we use a protein to bring things into the cell. Yeah, we're having a great discussion in the comments about the difference between facilitated diffusion and active transport. So let's actually do, let me get a whiteboard here, and we're going to compare these things because that's an important difference. Actually, before I do that, that's where we're going to go. Any last minute questions about the stuff that we have right here? We're going to do active transport versus facilitated diffusion, but any last minute questions before this disappears? Yeah, we're outlining active transport in the chat. Okay, well, I think, actually here, let's do this. If you feel good about this, can you give me a thumbs up emoji or some kind of happy emoji? So I know we're good to move on. I think we're probably good. Ah, dance party. I like it. Here we go. Let me give you my favorite. There's my favorite. Okay, so let's pull up a whiteboard then. So let's outline. We talked about facilitated, ooh, cannot spell yet this morning. Facilitated diffusion. Okay. While we're at it, let's see. Actually, start over. We are going to first compare passive transport. Let's go biggest picture. Passive transport to active transport. I saw some notes in the chat about this, so help me fill in my chart up here. When we talk about active transport, you guys told me it uses energy, right? So active transport uses energy. Does passive transport use energy? Do we need energy for passive transport? Yeah, no energy required. No energy required. Okay. When we talk about passive transport, we go from blank concentration to blank concentration. How does passive work? Blank to blank. Yeah, some of us that are new to office hours, that's a weird question for you. We talk about it a lot that way in office hours. High concentration to low concentration. So I always say blank to blank. We're going from high to low. So when I'm doing active transport, what words go in the blank? I'm going from blank concentration to blank. There we go. We're flipping it around. Low concentration to high concentration. Yep, low to high. Low concentration to high concentration. We talked about why this takes energy when we talked about the beginning of lesson number 4. So we did that analogy with the boulders on a hill. Think about having a boulder that's in a valley. It's down low, and we want to get it back to the top of the hill. You're pushing something uphill. We can think of it in terms of gravity. That's the way that going from low to high works. That's going to take energy. You can also think about it though, another analogy, can't remember if we did this in class or if I just thought of this. If you're at a grocery store right now and everyone is in their own aisle at the grocery store, right? There's tons of space. And then for some reason, they squish everyone into just 5 aisles of the entire grocery store. We're all spread out by ourselves versus now we're all in the same row. I don't know, maybe it's just me. But man, when I'm at the grocery store, that's when I'm around the most people. So I'm like hyper vigilant about how much space is between me. It takes some major energy on my part, like to watch the people around me when I've got a lot of people around me. So going from having lots of my own space, low concentration, to sharing my space with everyone, high concentration, that's going to take energy. So energy required for active transport, going from an area where there's not a lot to an area where there is a lot. Passive transport, no energy needed. Going from a place where there is a lot to a place where there's not as much. No energy required. I want you guys to help me list the types of passive transport that we've talked about in our class. What are the types of passive transport we've talked about in our class? Oh, nobody wants to type. There we go. I got a few people typing here. Okay, so one of the types we've talked about is diffusion. Okay. One of the types that we've talked about related to that is the facilitated diffusion. And the other type that we talked about is osmosis. Osmosis. Okay, let's start with explaining what osmosis is. What happens in osmosis? This process of osmosis. Yeah, so the big thing for us to remember with osmosis is that water moves. Or sometimes you'll see the word solute. Solute is just a fancy word for, oh, nope, I lied. It's not solute. Who can help me out in the chat? What word should I be putting there? Yeah, solvent, sorry. Solvent, the liquid. When we talk about osmosis in the body, what we care about is the movement of water. In chemistry, your chemistry teacher will tell you that osmosis can be the movement of any kind of liquid. So if we didn't use water to dissolve something, we can use the liquid in general, solvent. I know I do need more coffee, Christina. Man, it's real. I didn't start my coffee early enough today. So osmosis in our class, movement of water. If I don't want water to move, if I want my solutes to move, now I'm talking about diffusion. So movement of solutes, which is a fancy word, I'll put it in parentheses here, for dissolved things. If my things are moving, not my liquid, if my things are moving, then we're talking about diffusion. But not all things can move using diffusion. What are the special types of things, we just talked about this actually, that do diffusion across the plasma membrane of a cell? What were those words we used to describe the stuff that can do diffusion, to get into and out of the cell? Who can do diffusion? Yeah, so the stuff that matches the middle of the membrane, that's the stuff that can do diffusion. So that's things that are nonpolar, that's things that are hydrophobic, and we'll add our other thing to the list, things that are lipid soluble. Hey, I mentioned this in office hours earlier, but here is a major wink, wink, nudge, nudge. Make sure we know this. When I ask you on the exam whether or not something can diffuse across the membrane, you don't care what the name of that something is. You only care what I tell you about its chemistry. If I tell you it's lipid soluble, it doesn't matter what it is. That thing can diffuse across the membrane. If I tell you it's hydrophobic, doesn't matter what I tell you it is. That thing can diffuse across the membrane. Same thing with nonpolar. I can give you the weirdest name in the world and tell you it's nonpolar. You don't care what it is. If it's nonpolar, it can do diffusion across the membrane. So wink, wink, nudge, nudge. When I ask you on the exam if something can diffuse across the membrane or not, look for these words. Look for the words nonpolar, the words hydrophobic, the words lipid soluble. If I am any of these things, 100% yes, I can diffuse across the membrane. Now, if I am not these things, like we see right here, if I'm not these things, I'm going to have to do facilitated diffusion. When I do facilitated diffusion, remind me again, what's special about facilitated diffusion compared to regular diffusion? Yeah, facilitated diffusion is just diffusion plus a transport protein. It's the same thing as diffusion, it's just with a transport protein. If I have to use a transport protein, it's because my chemistry is wrong to just do regular diffusion. So what are some of those words we're going to use to describe things that have to do facilitated diffusion? What are some of those words like we listed for diffusion? Who's got to do facilitated diffusion? Okay, so I'm seeing some of the stuff like our list before. Oops, polar, hydrophilic, water soluble. I like that someone added to our list too, ions. Can't forget those ions. Yeah, and also large things. Yep, I should have included large on there too. Things that are large. Anything, so these first four right here, anything that doesn't match the middle of the plasma membrane, that's going to need a protein to get through. Anything that's too big, that would leave a gaping hole in the membrane, we're going to have to make a special protein channel for it. So facilitated diffusion is the same thing as diffusion. We just do it through a protein. Regular diffusion, we go straight through the membrane. No protein required. Osmosis, we're going, for the most part, here's a note I'll make for you. It's more technical than I'm going to ask you on the exam, but I'll mention this. Osmosis is technically, for the most part, a type of facilitated diffusion. It's technically mostly facilitated diffusion. In the chat, remind me, what does that mean? If it's facilitated diffusion, what happens in facilitated diffusion again? Yeah, we're all freaking out. Jacqueline's like, what? Yep, facilitated diffusion means we need a protein. That's all I was asking. It's diffusion plus protein. Okay, so check this out. Osmosis is the movement of water. Osmosis is the movement of water. What are some of those chemistry words that we use to describe water? Would we say water is polar or nonpolar? What is water? Yeah, water is polar. So for water to get across the membrane, for the most part, it's actually going to go through protein channels. Some water, to be fair, because you'll see this if you do a Google search, go down the Google bunny hole. Some water can go straight through the membrane because it's small. But most of the water that moves in and out of the cell uses a protein to do it. Fun fact, we have a special name for those proteins. Those proteins are called aquaporins. 100% not going to test you on that on the exam. Just a heads up for you though, because water is polar, because it is hydrophilic, I mean, it is water, right? So it loves itself. It's a little narcissistic there. Because it is water, again, it's all surrounded by itself. Because it fits this chemistry, for the most part, we're going to use proteins to move it in. But you don't need to worry about that. We just want to know that osmosis is when water moves. Water moves in osmosis. Facilitated diffusion is when we move some of these polar, hydrophilic, or all those kind of things through a protein. Diffusion is when we just go straight through the membrane because we match the membrane. Now, somebody kind of mentioned this before, and let me highlight it again. All of these types, so let's underline them here. Diffusion, facilitated diffusion, osmosis. All three of these things here, these are all examples of passive transport. Since we know that these are examples of passive transport, you can tell me every time that doing diffusion does not take energy, or that doing facilitated diffusion means I'm moving something from high concentration to low concentration. Or you can tell me in osmosis, again, no energy required. We're going from where there's a lot of water to where there's a little bit of water. So keep in mind when you're sorting things in your mind, these three processes that we talked about are passive transport, meaning there's never energy required, and we always go from high concentration to low concentration every single time. If we're trying to move something the other way, if we're trying to go from low concentration to high concentration, if we're pushing that rock up the hill, that is going to take energy. There is energy required to make that happen. We talked about two kinds of active transport. What were the names of the two kinds of active transport that we talked about? Yeah, so we've got primary active transport and we've got secondary active transport. To tie into Aaron's question for us, when we talk about primary active transport and secondary active transport, these are examples. We're going from low concentration to high concentration. Think of physically different locations. So something that's lower and something that's higher means I'm going up what's called the concentration gradient. Concentration gradient is the line that shows me the difference between these two. So something that's really low, something that's really high. If I want to go from low to high, I go up the concentration gradient. I'm talking about my passive transports. We're going from a high concentration to a low concentration. We're going down the concentration gradient. So that word concentration gradient, just think about it as the line between the two concentrations. When I go from high to low, I'm going down. When I go from low to high, I'm going up. So these two go up the concentration gradient. These three go down the concentration gradient. Now, primary active transport and secondary active transport, both of these are active transport. So that means that both of them need energy. Which of these two uses the energy of ATP? Which of these uses the energy of ATP? Yeah, so a lot of us have identified primary active transport. The energy for this is ATP in primary active transport. ATP, we joked about it in class. Think about it kind of like energy money. Here's an important idea that we mentioned in our class about ATP and about energy in general. I'm going to type it because it's so important. Here we go. If a cell uses energy to do something, I gotta like make little tabs each time. It must be important. It must be important. This is a big picture here. If a cell is willing to use energy to do something, it must be important for helping that cell to stay alive. So if the cell is doing the process of primary active transport, where it's spending its ATP monies, basically, to make something happen, that must be vital for it to stay alive. When we talked about primary active transport, what was the example, or what was the purpose of the protein that we said did primary active transport? What was our example of primary active transport? Yeah, Nicole mentioned its function. Polarizes the membrane. Yeah, and Christina mentioned for us there the sodium potassium pump. I put its full name for us in case we're a little dicey on our chemistry. Sodium Na, potassium K, pump. The sodium potassium pump was our example of primary active transport. The function of this pump was to polarize the membrane. That's a big, weird word. What does it mean if I polarize the membrane? What's going on with a polarized membrane? Yeah, so if a cell is polarized, that means it's different inside and outside. Different inside versus out. We said this a ton in our live sessions. A cell must be polarized for it to be alive. For it to be able to do its jobs, for it to be able to function, it must have a different charge inside versus outside. I don't make you learn a lot of numbers in our class, but I did ask you to learn the number that showed us that it's different inside and outside a neuron? What's the difference in charge on a neuron? Or in other words, what's the resting membrane potential of a neuron? Anyone remember that number? Yeah, good. Lots of us are trying. Most of the cells in your body have a difference in their charge inside versus outside of -70 millivolts. -70 millivolts. That means that inside the cell is 70 millivolts more negative than outside the cell is. It's more negative inside than it is outside. Our membrane must be polarized for that cell to be alive. If it loses this -70 permanently, that cell is dead. Sometimes we temporarily lose that -70 if we're a neuron to send a message, for example. We're going to look at that graph with that message. But this idea of needing to be different inside and outside, that's so important that my cell is willing to use its ATP, its energy money, to make it happen. So my first type of active transport is called primary active transport. My second type of active transport is called secondary active transport. And in secondary active transport, the energy that I use for it is, I'm going to type it in as somebody else's movement. We're going to call it somebody else's movement. What I mean by that is somebody else is going down their concentration gradient, so speeding down the concentration gradient. Somebody is going from where there's a high concentration to where there's a low concentration. When they go down their concentration gradient, when they're speeding around down fast, if I piggyback on them, if I jump on that energy of them going downhill, I can go up my hill because I'm using their energy. Yeah, so Tierney's asking if it's kind of like the Ricochet Effect. So if I understand what that means, which is a little dicey, I think what you're meaning is like if something hits a wall, it's going to bounce back in the opposite direction. So that's totally correct when we're talking about secondary active transport. Something bumps into something else and bounces the other direction. We talked about in class when we were talking about this secondary active transport, those things called Newton's cradles. So if you do a Google search, dude, guys, I got a problem. I'm going to be honest with you. I looked at, so we talked about Newton's cradle in class. 100%, I was so tempted to waste my energy monies on buying one. Like legit, I was tempted so hard to buy a Newton's cradle. For my friends who don't know what that is, if you do a Google search, it's one of those little things where you release a ball and it swings toward the left, hits some other balls, and then the one on the left side pops up, and then it swings back down. It goes back and forth and back and forth. I was so tempted, man. I'm really bad with my money right now because, you know, we're all locked down at home. So I almost wasted my energy monies on buying a Newton's cradle. Oh, Hannah says they have them at Hobby Lobby. Oh, Hannah, you're tempting me. I may have to go get me one from Hobby Lobby. So secondary active transport. The other thing I'll mention too, if you're having trouble understanding how this works, we did a whole session on the example, the boulders on the hill, where somebody rushes down the hill, bumps into their friend at the bottom of the hill, and gives them the energy for their movement to push them back up the hill. So the idea of a ricochet, or the idea of Newton's cradle, where one bumps into each other, sends the energy off that way, and then it sends the energy back this way, and we go back and forth. Whatever helps you to remember that in secondary active transport, we are not using ATP. ATP is not used in secondary active transport. What's used in secondary active transport is somebody else moving. So going down the concentration gradient, this rock rolling down the hill gives its energy to this rock to go up the hill. Secondary active transport. Now, let's do a little bit more in-depth comparison of these two types of active transport. So I'm going to clear off my whiteboard here. Primary active transport and secondary active transport. Remind me again, how do I power primary active transport? Where does that energy come from for primary active transport? Yeah, primary active transport, that energy is ATP. Secondary active transport, that energy was someone else's concentration gradient. Or rolling down the hill, rolling down the hill. On the homework assignment, when you were matching up the different types of transport, what you saw about secondary active transport, its description was something like this. One molecule moves down its concentration gradient. I'm going to abbreviate there. And one molecule moves up its concentration gradient. Help me out here in the chat. Which one of these, the molecule that's moving down or the molecule that's moving up, who needs energy? Which of these movements requires energy? Going down or going up? Yeah, it requires energy to go up the concentration gradient. No energy required to go down the concentration gradient. If I start pushing that rock at the top of the hill, it's gonna roll down without any energy required. If I wanted to go up the hill, that is gonna take me energy. So in secondary active transport, somebody moves, no energy required. Somebody moves, energy required. When I talk about primary active transport, what's going on with our ups and downs? When I do primary active transport, yeah, so in primary active transport, both molecules move up their concentration gradients. Both molecules move up. So let's go back to the example that we had of primary active transport here. Now I'll put it in the abbreviations to help us remember. Sodium potassium pump was our example of primary active transport, sodium potassium pump. When I talk about the sodium potassium pump, you might have to reference your notes for this, or maybe we've memorized it. Which way does sodium move in the sodium potassium pump? Which way does sodium go? Sodium goes, uh-oh. Good thing we talked about this. Sodium actually goes out. So we better talk about it. Okay. Let me draw. I know there was some chatter about this at the very beginning of our class time here. Some of us were here in class when we talked about the salty banana cells. Salty banana cells. If you weren't in class for that, we talked about it in lesson number 2. I recorded a special video about that. So if you missed our discussion of salty banana and this one doesn't cut it for you, you want to hear it again, there is a recording with that. For my friends who were here for that in our live session, when I talk about the salty banana cell, what do I have a bunch of on the outside of the cell? If it's a salty banana, what lives on the outside? Yep, so the two components of salt, right? So one of the components of salt is sodium. One of the components of salt is chloride. Sodium and chloride. If it's a salty banana, I've got a banana that I sprinkled salt on the outside of, that's sodium and chloride. Hey, what ion are bananas really high on? What do we have a lot of inside a banana? That's an ion. Thing with a charge, yep. My ion that's really high inside the cell is potassium. And then there were a couple of other things that we said we have a lot of inside. What else did we say we had a lot of? Yeah, we got a whole lot of proteins doing all kinds of stuff in the cell. Yep, and then we got that glucose. Hey, why is glucose good? What does a cell use glucose for? Yeah, glucose is the cell's favorite food. It's what it uses to make ATP. So we got a lot of glucose inside the cell. We got a lot of proteins inside the cell. We got a lot of potassium. Outside the cell, we've got a whole lot of sodium. We've got a whole lot of chloride. This, when you hear about the salty banana, this is the way that I like to remember what's inside and outside. When you think of a banana, bananas are high in potassium, and they naturally have a lot of sugar inside of them. We pretended that it's a super banana. So if bananas were 100% legit, they'd also have proteins. At least our cells have proteins, but bananas maybe don't. So analogy breaks down there. But if we have a salty banana, then we got this salt that we sprinkled on the outside. So when we are, I remember one of your learning objectives asks you to know what's going on inside and outside the cell. The way we talked about it in the lesson is the recipes for the fluids inside and outside the cell. Your salty banana is the way to go to help you remember that. Salt on the outside, potassium and sugar and proteins on the inside. The reason we talked about the salty banana is because it's going to help us figure out why certain things or why certain movements need energy. So let's go back to, we're starting out here with primary active transport. In primary active transport, we moved sodium and we moved potassium because it's the sodium-potassium pump. When we talk about the sodium-potassium pump, we got a little mixed up, so I'll help us out here. Sodium is going to move out of the cell in the sodium-potassium pump, and potassium is going to move in to the cell. When we're trying to figure out why the sodium-potassium pump takes energy, we need to look at the way that things would normally want to move. So for a type of transport to not take energy, we're going to have to be going from high concentration to low concentration. That's the only way for it to not take energy. So ignore this stuff right now. When I'm looking at my salty banana cell right here, my salty banana cell, I had a lot of sodium outside the cell. If I have a lot of sodium outside the cell, which way does it want to move? Into the cell or out of the cell, based on its concentration? Which way does the sodium want to move? Yeah, so we're a little nervous. I've got a high concentration outside the cell, which means I want to move into the cell. Naturally, no energy required. I want to go from where I have a lot of me, I have a lot of sodium outside, it wants to go inside where there's a little. High concentration to low concentration. If we did passive transport, sodium would go into the cell. Let's try this again with another one. If I do passive transport with potassium, where does potassium want to go? Does it want to go into the cell or out of the cell? Where does potassium want to go? Yeah, potassium wants to go outside because we've got a lot of potassium inside the cell. It wants to leave the cell, wants to go out. What if we were doing chloride up here? Which way does chloride want to move? Into the cell or out of the cell? How does chloride want to move? Yeah, chloride also wants to go in because it's more concentrated outside. We've got a high concentration out here and a low concentration out here. It wants to go in. Okay, this is normal. By the way, we need to make sure that this is why we need to understand the salty banana. This is why we need to know what I have a lot of outside versus what I have a lot of inside. Because if I know where stuff is concentrated, I know which way it wants to move. So I have a lot of sodium outside. That sodium, Am I back? Somebody said I went silent. Give me a thumbs up if you can hear me. Am I back? Okay. So what I was saying when I might have gone silent was, this is the reason that we need to know those recipes. So make sure you know what I've got a lot of outside and what I've got a lot of inside, because I could ask you to predict the way that something would move. If we know that I've got a lot of sodium outside and not as much inside, we know that sodium wants to go in. Or we know that chloride wants to go in because there's a lot outside, not as much inside. Or potassium wants to go out because there's a lot inside and not a lot outside. So if I do, I should type that for us here. If I do passive transport, my green arrows show us passive transport. That's the way that things move with no energy required when they go from high concentration to low concentration. Now, let's go back to the sodium-potassium pump. In the sodium-potassium pump, sodium moves out of a cell. When sodium moves out of the cell, it's going from where there's a low concentration to where there's already a high concentration. We have a lot of sodium outside, not a lot inside, and yet we're going to take anything that's on the inside and we're going to push it out. That's going from low concentration to high concentration. So energy is required. Let me type that. Energy is required for us to do this movement right here, to move that sodium outside the cell, because it's going from low concentration to high concentration. We also said that potassium moves in. I already have a lot of potassium inside, not as much outside. For me to move more potassium into my cell, we're again going up our concentration gradient. It's going to cost me energy to move my potassium in as well. Both of these ions move in a direction that need energy. Nobody's going down their concentration gradient. Nobody's coasting. We're both going uphill. Because both of us are going uphill, the only way I can make energy, I can use energy to make that happen, I've got to use the energy of ATP. I've got to spend my energy monies to make this happen. So I break up ATP, my energy molecule, so that I can move both of these guys in the wrong direction. Both of them are going uphill. I'm just going to have to tough it out, and I'm going to have to use my energy for it. Remind me again, want to make sure we know this. Why do I need the sodium-potassium pump? What's its job again? What's the purpose of this pump? Yep, the purpose of this pump is to polarize the cell membrane. The purpose of this pump is to polarize it. So to make inside and outside different. That's the goal of the sodium-potassium pump. The way that I make them different is by putting a whole bunch of sodium outside and a whole bunch of potassium inside. That's one of the big ways that I polarize my membrane. So primary active transport. What do we need to know about it? We need to know it uses ATP. We need to know that both things go up their concentration gradient. And if we know those things, that can help us predict why it takes energy, because both of these guys are moving up their concentration gradient. Now, in secondary active transport, I do not use the energy of ATP. That would be probably an underline, highlight, star thing to write in your notes. I do not use ATP for secondary active transport. My energy to make this kind of active transport work is somebody rolls downhill. And when they roll downhill, somebody else can roll uphill. So help me out in the chat. What was our example of secondary active transport? What was our example of this kind of transport? Do we remember? Yes, so some of us are mentioning the fun things that we talked about, Newton's cradle or hitchhiking. Sorry, I asked that question poorly. What I was looking for was the anatomy example, or the chemistry example, maybe we could say, of it. We all need more coffee, right? No, again, that was my fault. I asked a bad question. So the example that we had in our notes of what secondary active transport looks like is the sodium glucose cotransporter. So the sodium glucose cotransporter moves two things, and its name tells us the two things that it moves. It moves sodium and it moves glucose. Surprise! Let's remind ourselves though, and maybe you have these pictures in front of you here. When we do the sodium glucose cotransporter, which way does sodium move? Does anyone remember? Which way does sodium move in the sodium glucose cotransporter? Yeah, sodium moves into the cell, in. When we talk about the movement of glucose, which way does glucose move? Where's the glucose going? Yeah, the glucose is also going in. Okay, so check this out. Sodium moves in the sodium glucose cotransporter. Sodium moves in. Hey, there's a lot of sodium outside, and there's a little bit of sodium inside. This is an example of passive transport. So I'll make a little note for us here. For sodium to move inside, no energy required. For sodium to move inside, no energy required. What about moving glucose inside? New question. Do I have a lot of glucose inside or outside the cell? Where do I have a lot of glucose? Yeah, I have a lot of glucose inside the cell. So if we're talking about the way that glucose is going to move, if I don't use energy for it, I'm gonna dump that glucose. I'm gonna put it out in the environment. But we just said from our description of this cotransporter that glucose is going in to the cell. Glucose is going in. If glucose is going in, it's going from an area where there's not a lot to an area where there's already a lot. That particular movement, energy is required for glucose to move inside. Because I've already got a lot of glucose inside. A lot of glucose inside, put more inside, I need energy. A lot of sodium outside, let that sodium go in, no energy required. Sodium is the one going down its concentration gradient. Glucose is the one going up its concentration gradient. So some of the examples that you guys had from your notes, and some of us mentioned these things. Things like hitchhiking, see if I can spell, where somebody else spends their gas money and you just travel with them. Things like a piggyback ride. Let's be real. I got little ones around here, right? So we do the piggyback ride thing. Any kind of movement where you don't spend your own energy, you take somebody else's energy, because they're going downhill, they're releasing energy when they roll down that hill. If you can use that energy to move too, that's secondary active transport. So again, underline, highlight, star idea. There is no ATP powering secondary active transport. ATP is not used to make this happen. We use somebody going downhill to allow somebody else to go uphill. We don't use ATP to make that happen. Just like we said with the sodium potassium pump, there's an important goal or an important reason that we care about this sodium glucose cotransporter. What's the function or the purpose of the sodium glucose cotransporter? What does it do for a cell? Why does it use energy for that? We're questioning. Yeah, so a couple of us are chiming in on it. It has to do, so think about when we're trying to answer the question, what we're using energy to do. We're using energy to move glucose into the cell. The goal of the sodium glucose cotransporter is to feed the cell, basically, to feed the cell. Feed we're using loosely, right? This is the way that the cell gets glucose. The way that the cell gets glucose. And glucose is its favorite food. That's the easiest thing for it to make ATP with. So I'm willing to use energy, the energy of allowing some sodiums to come inside the cell. I'm willing to do that so that I can use that energy to get my food. Thumbs up, thumbs down. What questions do we still have? Good. I'm seeing a lot of thumbs up, a lot of got it's. I'm gonna stay paused for a minute though in case we're typing questions. No, so Gloria, the sodium glucose cotransporter actually doesn't have anything to do with the membrane charge. We're going to talk about that negative 55, but that is separate from the sodium glucose cotransporter. So here would be, that's actually an interesting note. Here, let's add this. Let me pick a different color here. These are both examples of active transport. Both of these processes use carrier proteins. Both of these processes use carrier proteins. Help me out in the chat. What do we know about carrier proteins? What's the deal with carriers? Yeah, so carrier proteins, they change their shape. Or another thing that we mentioned with them is they attach to what they transport. That's part of their changing their shape. In one shape, they're attached to what they transport, then they change that shape and they're not attached anymore. They're not always open, so open on one side at a time. Here would be a note that you should write down to help you with your studying. When you do active transport, you have to use carrier proteins. When you do active transport, you have to use carrier proteins. Let's see if we can make a connection here. When I do active transport, I'm going from blank concentration to blank concentration. What's the thing with active transport? Yep, I go from low to high. So when I do active transport, I go from low to high. When we use channel proteins, okay, here we go. I'm gonna erase my whiteboard here. You can all make a screenshot too in the video. Let's type this out here. Here's what we just said. When we do active transport, we use carrier proteins. That's the thing we just said. So when we talk about carrier proteins, here's some of the stuff that we said. We said that they change shape. We said that they attach to what they transport. We said that they open on one side at a time. And we also said that active transport, we do things from low to high. Okay, this is what we've said so far. When we talk about channel proteins, what's the name of the process that I use, the transport process I use with channel proteins? It is a type of passive transport. What's the special name for it? What's the special name for passive transport with channel proteins? Yeah, there we go. When we do facilitated diffusion, we use channel proteins. When we do facilitated diffusion, we use channel proteins. What can you guys tell me about channel proteins? What are some of the ideas about channel proteins? Kind of like we outlined with carriers. What's some of the stuff we know about those channel proteins? Okay, so when we say always open, we'll make a note here. That's the ones that are called leakage channels. Leakage channels are always open. We also have that are called gated channels. Gated channels, we have to open the gate. We'll talk about those gates. Yeah, a couple of us are noticing an important thing about those channel proteins. Do not attach to what they move. They do not attach to what they move. Hey, facilitated diffusion, is that active or passive transport? You guys have already told me this. Facilitated diffusion, yep, that's passive transport. That means that things go from blank to blank. Passive transport means we go from blank concentration to blank. Yeah, we're going from high to low. Important idea. Underline, highlight, star this. Channel proteins can only do facilitated diffusion. Channel proteins can only do facilitated diffusion. What that means for you when you're thinking about these types of proteins, they will always move stuff from high concentration to low concentration. Channel proteins can only ever move stuff from high to low. When we want to move something from low to high, because I'm doing something that takes energy, that's active transport, it takes energy, we're going the wrong way. The only way for us to be able to transport stuff the wrong way is I'm going to have to attach to what I'm moving, and I'm going to have to open up separately. Because see, with these channel proteins, at some point when they're open, whether they're always open or whether we open up the gate, their special kind of gate, whenever I have a channel protein that's open, 100% of the time, always, they're going to move stuff from where there's a lot of it to where there's a little of it. When I go from high to low, I'm doing passive transport. Channel proteins always do passive transport. If I'm doing active transport, it's got to be a carrier protein. I've got to change my shape and only open on one side at a time. Otherwise, if I open both sides, we're going from high to low. It's going to happen. And that's what happens with those channel proteins. They always move stuff from high to low. I need to know what we're thinking, what questions we have. Let me pause and let us think. Yeah, so Tierney mentioned there's no energy required with channel proteins. 100% correct. Yes. I'm gonna beat a dead horse here. This again is why we need to know salty banana. Salty banana. I'll make it for us here. Salty banana. Because when we're talking about which kind of proteins we're using here, if I'm using a channel protein, and this is true, well, the last thing we're going to look at here is that graph in just a moment. That graph that shows us what the membrane charge does, it's all about these channel proteins. Every time I open up a channel protein, it can only move stuff from high to low. We can only go downhill with these channel proteins. If for some reason I need to go uphill, I'm going to have to use a protein that can outsmart diffusion. I'm going to have to use a protein that says, even though you want to go from high to low, I'm going to make it happen where we can go from low to high. We gotta game the system here. And the only way to game the system is to change our shape to make it so that we can go the other way. Whoa. Did you all see that happen too? How did my cell move? That's funky. Yeah, magic, basically. So ignore that cell now, because now it's in the wrong place, right? Don't know what happened. I just am too magical, apparently. So keep in mind, I'm going to put it here in the middle, salty banana cells. Keep that in mind, because when you are figuring out passive transport, oh, that's true. Yeah. So when you're doing passive transport, we're always going high to low. We're always moving from where there's a lot to where there's a little. When we're doing active transport, we're always going from low to high. The energy comes from concentration gradients sometimes. Yeah, so somebody said the reason it moved is because my penguins are angry. I haven't drawn them yet today. Let me draw you guys a penguin. For my friends who are new to office hours, I try to draw a penguin every day. It doesn't always happen. Sometimes I forget. Hey, this penguin is looking legit. Look at this, guys. He's reaching for that banana. That banana went away. He wants it. Salty banana. There we go. We got our, yeah, he hates us now because he can't reach his banana. So there's today's penguin. We got a penguin today. Kelvin says he looks like an owl. I could see that. Yep. He's a macaroni penguin for anyone who's interested. These are the little yellow feathers he'd have coming out of his hair. Oh, Hannah thinks he wants a bow tie. We could do a bow tie. I also do, when I draw my little girl penguins, I give them little hair bows too. So here we'll give him a little bow tie. Give him a little hat. Matching hat. There we go. Okay. The one last thing I'm going to take some time to talk about with you guys is we're going to go through the graph at the end of lesson number 4. So let me pull up Yeah, someone says he looks amazing. That's probably the best penguin I've drawn all semester so far. So he's looking pretty good. When I try to draw them small, it really doesn't work. So he looks pretty good today. All right, here's what we're going to end on right here. Everyone's favorite, I'm saying sarcastically. Let's start looking at this graph. But yeah, he's dressed for success. Yes, he is. He's rooting for you guys, just like Dr. Allis is. All right, we are looking at a graph that says it's the membrane potential of a neuron. For my friends who've been to office hours before, when we use this word potential, what did I tell you guys to trade it out with? What's the easier word for what potential means? Yeah, so think about, instead of it saying membrane potential, you can mentally change it to, or even in your notes, you can change it to say membrane charge. Membrane charge. Remember that we said that the cells in your body are polarized. Let me put that polarized word on here again. Polarized. Polarized means it's different on the inside and the outside. So normally when your cells are polarized, when they're living their life, doing their normal thing here, they're at something called the resting membrane potential. Resting membrane potential. Oh, it's kind of gone. Here we go. Resting membrane potential. That's what you see right here where it says at rest and return to rest. This is just a fancy way of saying, hey, I've got a cell that's polarized, that's just chilling out. Nothing's really happening in it. It's listening to its neighbors. It wants to hear if there's a message, if there's a reason for it to freak out and talk to its neighbors. If a neuron receives a message and that message is exciting, it gets some hot gossip, that message might make the neuron change its membrane charge. When it's at rest, it's bored. It gets some exciting hot gossip here, stimulus applied, some hot gossip comes in. If that hot gossip changes what's going on the chemistry of its membrane, it might get all the way excited where it talks to a friend. When a neuron gets all the way up here to positive 30, when its membrane charge has switched from being very negative on the inside, negative 70, when its charge gets all the way up to positive 30, this is when a neuron can talk to its neighbor. This is when a neuron can send a message. Positive 30, though, is not normal, and it's way too exciting for this neuron. It can't stay here. So once it talks to its neighbor, it says, okay, we got to get back negative. Like, this is just too positive for me. And so it'll get back to negative, go a little extra negative, more than it needs to. But ultimately, it's going to end up back at rest, or back at resting membrane potential. So the first thing for us to know about this graph, the beginning and the end of the graph. This is when a neuron is normal, when it's listening, when there's not a lot going on. This part right here, the stimulus applied part, again, think about this when a neuron gets some hot gossip. Now, the hot gossip that neurons share with one another is in the form of what? I know it's a big, long word. How do neurons talk to each other? What are those special things called? Yeah, so neurons use a special kind of chemical called a neurotransmitter. That's how they talk to each other. That's how they get the hot gossip that they share with each other. So this part here that says that there was a stimulus applied, that's just a fancy word for saying one neuron spit out some neurotransmitters that this neuron we're looking at here received. Those neurotransmitters are a type of chemical, like I said. Hey, when those chemicals are released, yeah, Gloria beat me to the punch, right? When those chemicals are released, we open chemically gated channels. So neurotransmitters open up chemically gated, and in particular, it's chemically gated sodium channels. Chemically gated sodium channels. Chemically gated. When I have a gated protein, is gated means it's always or not always open. If we're gated. Always or not always open. I get the feeling that several of us are half listening because that was an easy question. Either that or we're all really afraid of gates. When we talk about a gated channel, whether it's chemically gated, voltage gated, or mechanically gated, doesn't matter. If it's gated, it's not always open. I have to open the gate. So the kind of channels, yeah, so when I apply my stimulus, when I do the right kind of chemical, the right neurotransmitter, that's going to open up a chemically gated sodium channel. We're going to do it again. By golly, by the end of this session, you're going to be so tired of salty bananas. I'll let you guys choose. Where are we starting? Inside or outside? We're going to hate them, but we're never going to forget. Inside or outside? Where do we want to start? Inside. Okay, got a couple votes for inside. Help me out. What's inside this salty banana? What do we got in here? We all better know this, right? Man, by the end of this session, we can do this in our sleep. That should be K+. Sorry about that. I am doing it in my sleep, apparently. K+, proteins, glucose. Perfect. Okay, that's inside. What's outside? What do we got on the outside of this salty banana? Yep, sodium and chloride. I think on the last day of class together, we should all do the salty banana challenge. Like, we should all get a banana and put a little salt on it and eat it together, like on camera. That would be so fun, right? Not really. It would be really terrible. But it would be a bonding experience, right? So, no, thank you. Yeah, making memories, right, Hannah? That's what I'm saying. Let's make memories together. So, okay, if you don't know the salty banana by this point in time, like, come on, guys, get with the program. Go eat yourself a salty banana and you'll never forget. So, the reason we did the salt, we outlined our salty banana again, is because check this out. Chemically gated sodium channels. Now we're going to focus on the sodium part here. Chemically gated channels do passive transport, meaning we take things from high to low. When I open up a chemically gated sodium channel, which way is sodium going to move? Where's sodium going if I open up a chemically gated or just a gated channel protein? Yeah, sodium's going to go inside. It's going inside because I've got a ton of it outside and not a lot of it inside. Okay, so I open up a channel for sodium. Sodium comes in to my cell. Sodium is a cation. It's got a positive charge. When I bring that positive charge inside, I was at -70 inside. Now I do +1, +2, +3, +4. Sodium has a positive charge. The more of those little positives that I add up here, the higher the charge on my membrane gets. So the first kind of channel we're talking about here are channels that have a chemical key. That chemical is the neurotransmitters that neurons use to each other. So I open up this channel for sodium. Sodium wants to come inside, and sodium brings its positive charge with it inside the cell. Now, here's another number. Like I said, don't make you know many numbers. We got to know this one. Resting membrane potential, normal. Second number we need to know is -55. -55. This is something called the threshold value. The threshold value is when the membrane charge gets different enough that I open up a new kind of gated proteins. These are gated proteins that open when the charge is wrong. What's the name for proteins that open when the charge is wrong? What kind of gated are those guys when they open for charge? Yeah, if I open because the charge is wrong, it's voltage gated channels again. We are still talking about voltage gated, we're still talking about sodium channels, but now we're talking about the voltage gated ones. When we hit threshold, when my membrane charge is different enough from normal, when I'm at 55, I'm far enough away from 70 that my proteins that are all about the charge are going to open up. They're going to freak out. They say, okay, the charge is different. I'm supposed to open here. Voltage gated sodium channels. When these channels open up, promise this is not a trick question. When I open up a voltage gated sodium channel, which way is sodium going to move? If I open a voltage gated sodium channel, yes, sodium is still going to rush inside. I still have way more outside than I have inside. Now I'm going to open up the voltage gated channels, the ones because my charge is so different, I'm going to open it up and rush in tons and tons and tons of sodium. And again, because sodium has a positive charge, we're going positive, positive, positive. We keep bouncing up positive charges until I get all the way up to positive 30. I have so much sodium inside of me, my membrane charge now on the inside looks positive. It used to be negative, it's positive now because I have so much sodium inside my cell. And this point up here, positive 30, that's the last number for us to be familiar with. When a cell hits positive 30, we would say that that cell is depolarized. It's completely opposite of normal. It's depolarized. So the left side of the graph, you had a question on the homework that said which part of the graph shows depolarization. This whole part over here is the part of the graph that we're showing depolarization. Technically, it includes this part down here too, if we're being fair. So depolarization is where we're making the membrane charge go up. When the cell gets all the way to positive 30, now we're depolarized. We're completely wrong. My charge is completely wrong. I need to get my charge normal again. I'm going to open up more channels that open because of charge problems. Again, what's the name of channels that open because my charge is wrong? What kind of gate opens with charge issues? Yeah, it's still voltage. Yep. Charge issues is always voltage. So voltage gated this time, we're going to have voltage gated potassium channels. Now we're doing voltage gated potassium channels. Check out my salty banana over here. If I open a channel for potassium, which way is potassium going to move? Where does potassium go when I open a channel for that? Exactly. Potassium is going to go out. Now, this is where it's a problem that I put an equal sign there, right? Okay. Potassium is plus, K plus. Okay. So potassium, we opened up a channel for it. Potassium is going to rush out. Potassium still has a positive charge, but it's leaving. I'm basically doing subtraction, if you will. So I lose a positive one, and I lose a positive one, and I lose a positive one. I lose all of these positive potassiums. I'm spitting them out. Got to spit them all the way out because I'm trying to get back down to negative 70. So I'm going to spit out as many potassiums as possible. When they leave my cell, they're going to take their positive charge with them to get me back down to the negative range. We will talk more about this in Unit 3. We're so good at spitting out potassiums that we actually spit out too many, and we get lower than resting membrane potential. At that point, I'm going to use leakage channels, and at that point, I'm going to use that sodium-potassium pump to rebalance things and get back to normal. But this side of my graph over here, this side of my graph, we're doing the process of repolarization, where I'm making my membrane charge go back down negative. So repolarization is the other half of the graph here, when I bring that charge back down. And I repolarize the membrane by spitting out potassium. That's the positive charge that I can spit back out. Let me check my chat here. So think about the sodium as being a bully. Sure, that'd be a good way to remember it. If you got big bad sodium that rushes into the cell and it forces potassium to leave. Potassium gets bullied and makes it leave the cell. I like that. That'd be a good way to remember it. The question, when voltage-gated potassium channels are open, does that mean the voltage-gated sodium channels close? Yes. So kind of. Let me pull up a picture to show you guys. It's one of the last pictures that you have in your lesson number 4 outline. This picture right here that shows you the 2 types of voltage-gated channels. On the left, we have voltage-gated sodium channels. On the right, we have voltage-gated potassium channels. Voltage-gated sodium channels have this special little thing right here. So see this little thing called the Inactivation Gate? It's kind of like a stopper in a bathtub. So when we are depolarizing our membrane, when we're trying to make the charge positive, we use the voltage-gated sodium channels to let a bunch of sodium inside, and that makes it positive on the inside. When we get all the way up to positive 30, this little stopper, this little bathtub stopper, actually wedges itself into the voltage-gated sodium channel. Now the voltage-gated sodium channel doesn't have a space for sodium to come through anymore. So it's inactivated is basically the way that we would say what's going on with it. There's too much sodium inside, which causes this part of the protein to change its shape and put a stopper in it. It says no more. We cannot handle any more sodium, and only potassium is moving at that point. Gloria asked if these particular pictures are on the exam. These pictures are not in particular, but the ideas that they represent are. So which kind of channel proteins are open when on that graph that we were looking at? This is a picture that shows us those types of channels. It also shows you, for your reference, our salty banana. Here's that sodium on the outside. Here's that potassium on the inside. So just a visual representation of some of the stuff that we chatted about. We are about out of structured time. Yeah, salty bananas everywhere, right? I'm telling you, man, maybe a few of us can be brave in December and we can do the salty banana challenge together, because it is everywhere. It's perfect. We're going to see it a ton in unit number 3. So learn it for unit number 1. It's coming right back up in unit number 3. Esley asked, on the test, will you specify what kind of voltage-gated channel you're asking about? Yeah, so let me back up here. Where you're going to see questions about these types of channels, definitely with this graph. So I might ask you on the exam, which kind of channel is open right here? Or which kind of channel is open right here? So I wouldn't necessarily tell you, because I'm asking you to tell me, or I could ask you the question, which kind of channel do we use to repolarize the membrane? Or I could ask you, which kind of channel do we use to depolarize the membrane? So if you can pair up the words like depolarize and repolarize with the parts of the graph, and if you can remember which specific kind of channel is open at different parts on this graph, you should be prepared for those kinds of questions. What other questions do we have? How are we feeling now? Give me an emoji or give me some text. Are we feeling a little better for the exam? Are we still freaking out? Where are we at? I blew Kai's mind today. Erin feels good. Nicole's thumbs up. Feel better. Yeah, Christina says at least she feels better about the graph. That's perfect. Keenan's got a lot to think about. Hannah's feeling good. That's perfect. Let me mention one last thing before I turn off our recording here. For when you're ready to take the exam, couple of quick notes. Number one, if at all possible, try to be plugged in to the internet. If your internet dies during the exam, it's going to kick you out of the exam. So you'll have to get in touch with me and I'm going to have to re-let you back in. You might have to start over. So please try to be plugged into the internet or have a really stable connection. Next thing with that exam is you are going to have your webcam going during the exam. I promise I'm not a creeper and I don't go through and watch all the videos unless it's flagged for me. So make sure your webcam is on and it needs to stay on and facing you the entire exam. Like we mentioned at the beginning, you've got 75 minutes to take that exam. So if you hit a question you don't know the answer to, skip it and go back to it. You've got time at the end to go scroll back through and just make sure that you've put an answer in for all of your questions. If you have not already downloaded Proctorio onto your computer, there are directions for how to do that. You have to take the exam in Google Chrome because that's the only browser that Proctorio works in. So download Proctorio. Go into our class when you're in Google Chrome. Before you'll even be able to see exam number one, you're going to have to take a practice test, quote, quote, practice test. It's literally one question that asks you if you have Proctorio downloaded. So the purpose of that test is to make sure that Proctorio is working on your computer. If Proctorio asks you for a password, that means that Proctorio is not working on your computer. So there's a troubleshooting document about how to get it working. So if you click on that practice test or you click on the regular test and it asks you for a password, don't email me asking for the exam password. I don't have it. Proctorio is the only one that has it. So until Proctorio is working, you're not going to get past that password screen. So there's a troubleshooting document for you. Go through, there's like 12 different ways to troubleshoot it. And if you get through all of those and you still can't make it work, then get in touch with me and maybe we can figure it out together. But we need to have Proctorio working to get that practice exam working and to get exam number one working. Corollary fact related to that, you will not see exam number one in your folder until you've taken that practice test. So I'm not going to let you take exam one until you've taken the practice test. So make sure you can go in now and take that practice test just to get it over with, to make sure Proctorio is working. Until you've done that practice test, you won't see the real exam. Gloria mentioned if we need to close all the tabs. For the real test, it's going to make you do that. For the practice test, it won't. The practice test is just going to kind of be a dry run to make sure Proctorio is activated. But yeah, for the real exam, we got to close all the tabs. Make your screen really big so you can see it as big as possible, because you're only going to be allowed to have that one tab open. Erica asked about scrap paper. So I gave you a whiteboard in the exam that you can use. If you would prefer to use a scrap paper, here's what I need you to do. At the beginning of your exam, I need you to hold up that paper and show me the front side and the back side to show me it's completely blank. At the end of the exam, I need you to hold it up again to show me the front side and the back side. And I need you to rip it up for me on camera, just for exam security purposes, just to make sure that I see that we're not sharing it with friends. So I hate that I have to say this, but if you guys see some funky stuff popping up in the group me, AKA, hey, look, these look like exam questions, please let me know. That's not okay, right? We're all on the same page that we're trying our hardest, we are studying, and we're putting the work in. If we see some funky stuff happening, please do reach out. In case it was in question, that's not okay, right? To share questions. So just do me that favor. So Gloria asked, to be clear, there'll be 2 tabs, Proctorio and the exam. Yeah, I believe Proctorio, either it has a little tiny tab, or it'll show you what the video looks like. So yeah, it might be 2 tabs. I'm not sure exactly what it's going to look like, but you'll be able to see what your webcam is showing at all times, and then you'll have your exam screen in front of you. Yeah, I see a lot of comments about missing the classroom. I'm 100% there with you guys. I miss being with you, so I feel your pain too. Jacqueline asked, when will unit number 2 be on Blackboard? As soon as you finish exam number 1. So if you take exam number 1 now, you can pop right into unit number 2. If you wait until tomorrow to take it, it'll pop up after you take that exam. So whenever you take your exam for unit number 1, unit number 2 will pop up for you. And Gloria asked when it will be graded. Yeah, it's graded instantly. The computer's going to grade it for you. So you will see your percentage score right away. Yep. All right, well, we are about wrapped up, I think. I will mention that following, I think it's at 12 o'clock or 12:30, maybe someone can help me out, when the SI session is today. Is it at 12? If you want to do, yeah, so it's at 12. If you want to do another review in a different way, our supplemental instructor, Elise, is hosting a review session today at noon. So if you haven't been to her sessions before, you access those using that Start Here area of our class. There's a link that says about our supplemental instructor. You can click into there and find that session too. So if you want to do a little more review, that's 12 o'clock today. I'm also available via email. I'll be chilling out here in the room waiting for any questions you have today from 5 to 6:30. Tomorrow morning, we're going to do lab stuff for the week. So if you have a chance to look over lab stuff, maybe try to give it a shot. If not, that's okay. You can still show up anyway tomorrow at 9:30. So best of luck to all my friends who are going to take the exam today. And if you have any issues, please reach out via email. Just recognize that I don't usually stay up all night. So I'm probably not going to reply in the middle of the night, but I'll reply as soon as I can. So yes, good luck to everybody here. I'll draw you one last good luck penguin here. Oh, he's not going to look as good. See, we set the bar so high with that one that looked awesome earlier, and then this one is going to be like demented. This is going to be the one that's like hopped up on caffeine, like you guys all are, right? So here's our little penguin friend, and he's going to say for you, good luck. Good luck. All right, well, I'm going to shut off my recording. I'll stick around for questions, but yes, best of luck to you on the exam.